So we've already done systems of equations. Why don't we do systems of inequalities as well, and linear inequalities, because those are much easier to work with. So if we take a look here, we're going to do a lot of graphing now. So if a line is in slope-intercept form, it's easy to graph, right? Like in this case, I can graph the y-intercept at -1. Then I can use the slope from -1. Remember, I got a rise of 2 and a run of 3, rise over run. So up 2, right 3. And there's a point. Remember, I could also go down 2 and left 3, because that's also a positive 2/3. So down 2 and left 3, and there we go. I got a line. Okay, so just remember, if it's slope-intercept form, nice and easy to graph. Just be careful, the way it's written. So in this case, what is my y-intercept? Well, it's the number by itself, 3. So I'd come up here, and what's the slope? Well, it's -2. It's the number in front of the x. Remember, I need a fraction, so -2/1. So that means I'm going down 2 and right 1 because of the positive. So down 2, right 1. Remember, I could also switch the negative. I could go 2 over -1. It means the same thing, right? Because if the negative's out front, I just give it to one or the other. I don't give it to both. So I could have went up 2 and left 1 as well. All right, so slope-intercept form's nice. Even when it's standard form, right? Remember our standard form, ax plus by equals c? Instead of taking all the work to get it in slope-intercept form, we could just find the x-intercepts and the y-intercepts really quickly. Okay, we have some rules. To find the x-intercept, all I got to do is take c divided by a. There's a quick trick to that. And to find the y-intercept, I just take c divided by b. Or the long way is to find the y-intercept, I plug in 0 for x. And to find the x-intercept, I plug in 0 for y. So two ways to think of it. If you know the quick trick, it's kind of nice. So if you notice, we got standard form, right? ax plus by equals c. So one way to do it, the longer way, if I want the x-intercept, well, that's when y equals 0. So I'd plug in 0 for y. So I'd say 2x minus 3 times 0, which, minus 3 times 0 is just 0, so that's gone, equals 12, and so x must equal 6. So I could put a dot at 6, where x equals 6, right? Remember, the quick way for the x-intercept is just to take the c over the a, the number in front of x. So all I had to do was take 12 divided by 2, right? The c over the a, and I could have got 6 right away. So for the y-intercept, let's go ahead and do that. It's just the c over the b. Well, what's the c? That is 12 over -3, so that's -4. Right? Because really, once I plug in 0 for x, that's gone. So 12 divided by -3 gives me -4. And that's the y-intercept, so down to -4, and there I can draw in a line. So even when it's in standard form, instead of writing it all the way in slope-intercept and taking all that time, if you remember your quick trick, or if you remember, x-intercept, plug in 0 for y, y-intercept, plug in 0 for x, you can find 2 points pretty easy to graph. Okay, so knowing that, now we're going to get rid of these equal signs, and we're going to put inequalities. Graphing does not change. We graph it the exact same way. So this is slope-intercept form, even though it has an inequality symbol, so I graph it the same way. So I put y-intercept at -2, and I use my slope of 3/4, so a rise of 3 and a run of 4. So I go up 3, right 4, or down 3, and left 4. And I draw on my line. Okay, now here's a couple things. The lines. I'll explain this here in just a second, but if there's an equal to with it, we need a solid line, which in this case I do. It's solid. Okay, if I would not have an equal to, so like a greater than or a less than, we do a dotted line. We do a dotted line, and I'll prove that to you in just a little bit why that is. But for now, let's not worry about it. So I got a solid line since it's got an equal to. And then with inequalities, the thing is, you need to shade one side of the line or the other. Well, to figure out which way to shade, we want to shade the side where points work. Well, what do I mean by points work? Well, that means we're going to test a point. Okay, we're going to test a point. So we pick a point that's not on the line. So for example, the one I usually like to pick is 0, 0 if it's not on the line. That's a great point to pick because it's easy to plug in. So if I test 0, 0, so I'm going to do that over here. I'm going to test the point 0, 0. So I basically plug that in. I plug in 0 for y and 0 for x. So I get 0 is greater than or equal to, well, 3/4 times 0 is 0, and 0 minus 2 is -2. And then I just look, does that make sense? Is 0 greater than or equal to -2? Yes, it is. 0 is greater than -2. So since this point worked, every single point on that side of the line works. So this point would work if I plugged it in. This point would work. This point would work. All these points would work. So we shade this side. We basically color it in to show that all these solutions work. And guess what? Since I have a solid line, any point that I would plug in right on the line would work as well. That's why this equal to is here. And we'll show that to you in just a bit. So we just shade the side that works. If I would test a point on the other side of the line, it wouldn't work. And let's just show that to you here. So if I were to test a point that was on the other side, for example, 2, -2. Let's try that. So I'm going to plug in 2, -2. So -2 for y, 2 for x. So I'd get -2 is greater than or equal to, well, 3/4 times 2 is, so this becomes a 2, that becomes a 1, so I got 3/2. It was 6/4, which simplifies into 3/2, and -2. So -2 is greater than or equal to, and this I could replace with 4/2. So I got -1/2. Well, is -2 greater than -1/2? No, it's not. It's not greater than. So that does not work. So that means all the points on this side do not work, don't work for this inequality. So that means I would shade the other side. Okay, so when you test a point, if it works, you shade that side. If it doesn't work, like it just did here, this point did not work, so I shade the other side. All right, let's keep looking at this. Oh, we got standard form. So guess what? For standard form, we use our quick trick. So we graph the x-intercept, which remember we just take c over a, right? Here's my c, here's my a. So I take 6/2, which is 3. So an x-intercept of 3 crosses the x-axis. And we do the same thing for the y-intercept, except now it is, what's the trick? C over b. And what's the b? -3. So 6 over -3, which is -2. So go down to -2, and there we go. We draw on our line. It's solid because of this equal to right here. There's an equal to with it, right? I'll explain that in a sec. And now we have to test a point to figure out where to shade. What's a good point to test? Yeah, 0, 0. It's not on the line, so I'm going to test 0, 0. So I go up here, I plug in 0 for x, so I got 0, right? 2 times 0, and then 0 for y, so 3 times 0 is 0. Is greater than x. Well, is 0 greater than or equal to x? No, it's not. So all the points on this side don't work, so that means I need to shade the opposite side. So all the points down here would work. There we go. Okay, so what is the difference between these two? They both have a y-intercept of -1, and they both have a slope of 2, so I'd go up 2, right 1, or down 2, left 1. Up 2, right 1, down 2, left 1. But the only difference is if I pick a point that's right on the line. So for example, right here, this point 1, 1. Let's plug it in. I'm going to plug in the point 1, 1 for y and x. Let's see which one it works. So 1 is greater than or equal to, well, 2 minus 1, which is 1. Is 1 greater than 1? No, it is not. Okay? How about over here? 1 greater than or equal to 2 minus 1. 2 minus 1 is 1. Is 1 greater than or equal to 1? Yes, it is. Right? 1 is equal to 1. So that works. So that means when there's an equal to for our symbol, right? We got an equal to with it. Greater than or equal to. We have a solid line. So solid for equal to. So less than or equal to or greater than or equal to. Well, the other side, we didn't have an equal to. So for greater thans or less thans, we need a dotted line to show that points on the line do not work. So I put a dotted line for that. So now points on the line do not work. Okay. To graph them, I would still shade, right? So I would still test a point. In this case, I'd like to test 0, 0, since it's not on the line. And basically, is 0 greater than -1? Yes, it is. Is 0 greater than or equal to -1? Yes, it is. So they would still have the same shade, but one has a dotted line and one has a solid line just because of the symbol. Okay, so be careful with that. So when we do a system, all we do is we graph them both, and then we find where they overlap. Okay, where like the shades intersect each other. So for example, like this. So I deal with one at a time. So this first one, I go graph it, y-intercept of -2, slope of 1/3, so up 1, right 3, or I could go down 1, left 3. And it's dashed because of the inequality doesn't have an equal to, so you notice my line is dashed. Then I do the same thing to the other one, y-intercept at 3, slope at -2, so -2 over 1, so down 2, right 1, or I could go up 2, left 1. And it's solid because there's an equal to, so I got both those. So now I have to shade each of them individually. All right, so let's do that. So let's go up to this top one. Can I test 0, 0 for this dotted line? Yeah, it's not on the line, so I'm going to test 0, 0. Well, 1/3 times 0 is 0, and 0 minus 2 is -2. Is 0 greater than -2? Yes, so that works. So I need to shade on the side where that point is according to this line. So I'm looking at this dotted line. So I'm going to shade above that line. Okay? So now I do the same thing to the other one. Can I test 0, 0? Yeah, it's not on the line, so I can test 0, 0. So 0 less than or equal to 0 plus 3. Is 0 less than or equal to 3? Yes, it is. So I shade on that side. Where was this point? Good. What line am I looking at? I'm looking at this one right here, right? This black solid one. So I got to shade on the side where that point's at. So this is kind of harder to do since you already have a mess, but it's all of that right there. Well, then my solution is where they combine, where they intersect, right? So if I look, right here, this section is where they combine to. So this would be the solution. All right, so we see that. So the green would be the solution, right, where the two things combine. Oh, now I got going way too much over here. The green shouldn't be on that side. So just right in this region right here, from the dashed through the solid right here is where the shade would be at. Okay, and I can also do this on a calculator. Let's check this out. All right, so if I grab my calculator, I'm going to y equals, and I'm going to graph both these equations. So 1/3 x minus 2. I'm going to go zoom standard, number 6. Okay, so if you notice, they're both solid lines and there's no shading. Okay, well, to get the shade, what we need to do is, so right now, if you notice, they're both solid lines. So as I hit enter, I just go over here and I hit enter, and I start getting different things. I got a dark line. Oh, this looks like a shade. That looks like another shade. Which one should I do? Well, there's a dotted line. We're not going to worry about the dotted lines, but I like these shadings. So which one should I do? Should I do this shade? What do you think that would mean? Should I shade above or below the line? This one would mean above the line. Well, what do I do? This is for the dotted line, right? Did I shade above or below it? Yeah, we shaded above. That was the red. So we shaded above. So I'm going to keep that just like that. So let's just graph that just so we can look. Oh, there we go. It's shaded above that line, right? That's that red that we just did. Okay, now I still need a shade for this one. Well, am I going to shade above it or below it? Look over here. That was the blue. We shaded below it, right? So let's go back to y equals. And I'm going to scroll over. So I want the shade to go below. So now I choose this one to go below, right? It looks like it's going below. And then I hit graph. So the first one shaded above. Second one shaded below. And there's their intersection right there. So you can check your answer on your calculator just like this. Well, sort of. You still have to test a point, right? You still have to test a point to figure out whether you shade above or below. But that's kind of cool that your calculator will actually do that. Okay, but just pay attention to whether it's dashed or solid as well. And last thing, we have something called the feasible region. And the vertices of the feasible region are important. So I'm going to quickly graph these guys. So if I graphed y is greater than or equal to 2, that's going to be a solid line. And I'm going to go where y is 2. And I'm going to make my line. I'm going to graph that first, so it's like this. And we're saying greater than or equal to, so that'd be above it, right? Numbers that are greater than 2. So this would be shaded right there. And then I'm going to graph this one. So x's that are from 0 to 6. So first of all, I'm going to graph kind of like that line. X is greater than or equal to 0. And I'm also going to graph the line x is less than or equal to 6 because I'm looking for points in between there. So I'm going to put a line where x is 0. So it's going to go through x at 0, and it's also going to go through x at 6. And they both have equal to's with it, so I need solid lines. And that would be stuff in between there, right? So all of this just like that. And then lastly, I have something in slope-intercept form. So I need the y-intercept at 6. So that'd be right here. and I need a slope of negative 1/4. So remember, I have to give either the negative to the top or I have to give it to the bottom, one of the two. So I can either go negative 1/4 or 1 over negative 4. So I could go down 1, right 4, or I could go up 1, left 4. And I still got a solid line because I got the equal to, so just like that. And what I shade above or below, well, you can actually kind of look at your inequality symbol and tell it's less than or equal to, so that should give me the sense that I'm going to shade below. If I tested the point 0, 0, if I tested that point, I'd have what? 0 is less than or equal to 6 minus 1/4 times 0, which is 0. Is 6 less than or equal to 0? Or 6? My fault. Yes, it is. So I would shade below. So you can actually just look at that symbol and should be able to tell. So I shade below the green line, which is like this. And then, remember, the solution to the system is where they all intersect at. And if I look, where do the red, white, and blue intersect at? Yeah, right in here. In this region right here. We're going to stay inside that red line, that blue line, and that green line. Right where they all intersect. So that is what we call the feasible region. This is the feasible region right here. And we designate the feasible region by its vertices. So what are the vertices here? I got 0, 2, 0, 6. So I'm going to write these down. 0, 2, 0, 6. And then I got, this is where it gets a little bit tougher, right here and right here. So this one I can tell this is at 6 and up 2. So I got 6, 2. And what would this one be here? Well, let's think about it. I have, let's follow my green line. So I was at 0, 6, and then I went down 1, right 4. So really I'm going right 2. So instead of going down 1, I'd go down half, right 2. So it'd be halfway between 4 and 5 there. So this would be 4.5 for its y value. So I probably went too fast on that, but hopefully you can think through, pause your video and really think through that one using your slope and an x value of 6. So those would be my 4 vertices for that feasible region right there. And that's all there is to it with our system of inequalities.